Okay, so have a look at page 20. You have two coils C and D that are placed close to one another here. Each of these are solenoids, but only one of those solenoids actually has current flowing through them. That one will be coil C. So coil C itself has current flowing through the coil, whereas coil D actually does not have any current flowing through it. What it is connected to is just a voltmeter. All right.
Yep.
So here they're telling you that the variation with time t of the current I in the coil C is as shown in figure 5.3. They're varying the current inside the coil. Then on figure 5.4, show the variation with time of the EMF E induced in coil D for time 0 to T5. So what you're looking at here in the first graph is the variation of current versus time for coil C. But then after that, they want you to deduce the shape of the graph showing the variation of EMF with time for coil D in the second figure, which is this one here. Okay, right. So this one here, the variation of the current inside the figure, variation of the current in coil C. We all know that in the first place, whenever you have a, maybe I should just draw it on the diagram here. Wait, give me a second. Okay, right. For our case here, because we have coil C like this is coil C, which is connected to a power supply. And then after that, we have coil D here, which is connected to a voltmeter. They say the coil C actually has current running through the coil like this. All right. When current runs through the coil C itself is going to generate its own magnetic field. So the coil will actually generate a magnetic field, which may probably look like this. Okay. Provided your coil D here is placed close enough with the coil C here, you're going to have magnetic flux linkage. Okay, then it could be that the magnetic flux from coil C links to coil D. Okay, so this one here, there is flux linkage. Okay, and we know that rate of change of flux linkage produces EMF. So here, when we have current varying like this, we're actually causing the magnetic field, the magnetic flux in coil C to change. But at the same time, because it's linking with coil D, whatever change in magnetic flux density or magnetic flux in coil C will also be experienced by coil D. So coil D now experiences a change in flux linkage. It's going to have EMF induced. That's why the second figure here in your page 21 is asking you to draw out the EMF induced. Okay, so there are a few things that we can do from here. The first thing we can probably say here is this. For a solenoid, I know that B is equals to mu naught IN. So mu naught and N is constant. This would mean that B is proportional to I. This is the first relation. This one is for the solenoid, for any solenoid. This equation here was something that was given in your magnetic field chapter. I mentioned that this equation is not really required for you to memorize. It's just that it's useful to know because it helps you to explain certain things. Okay, but let's just say you don't remember it, never mind also. All you just need to know is that flux density has a relation with current. The higher your current that runs through, the stronger your magnetic flux density, the stronger your magnetic field strength. So this is point number one. Okay, point number two would be this one.
What does mu naught represent? If
mu
we were
naught
to
here
key
represents permeability
Oh, right, right. Okay.
or free space.
Mm,
Okay, it is permeability of free space. Actually, you can see it from the first page of your, second page of your question paper every time.
okay.
It's actually the second line here, permeability of free space. It's just a measure of how easy it is for magnetic field to pass through a medium. In our case, our medium here is vacuum, so that mu naught is the value there. Okay, but you're not really required to explain what is mu naught, what does it mean, what does it do, and so on and so forth. Okay, so that one should be okay, no worries there. Okay, now, so back to the next point. Another thing that we could also say here is this. We know that flux linkage is NBA. So if we say that A is constant, flux linkage is actually proportional to B. Okay, this one will be proportional to B. Okay, so
Okay.
if we add these two relations together, relation 1, relation 2, we're going to get a case where flux linkage is actually proportional to
Current.
current. That's how we get to this conclusion here. Okay, our flux linkage is proportional to current. Okay, so while this graph here for coil C shows us the variation of current with time, it can also be thought of as a graph of flux linkage versus time. In terms of the shape will be the same, because here we've managed to see that flux linkage is proportional to current. So if current is constant, flux linkage is constant. If current increases, flux linkage increases. If current decreases, flux linkage will also decrease. So in terms of the shape of the graph itself, if a graph of I versus T gives us this, a graph of flux linkage versus time will also give us the same shape. Okay, so now from here, we would go on to the next part, which is this one. Now, the third thing we also know is that EMF is actually rate of change of flux linkage, which in a way is actually the gradient of our flux linkage versus time graph. So now over here, we actually already have the graph of flux linkage versus time. Okay, so this flux linkage over time graph is the flux linkage in coil D itself. Because just now I mentioned that whenever you produce your magnetic field here, provided your coil D is situated close enough to coil C, the magnetic flux here will link to the adjacent coil. So you have flux linkage here, right? So in your case here, your coil D is experiencing a change in flux linkage, therefore you're going to have EMF induced. So here you know that your EMF is actually your gradient. So there are a few things on there that you can then do. The first one here, you can see that here is gradient 0, therefore EMF is 0. This one here, gradient is 0, therefore EMF is also 0. And same goes with this one, gradient equals to 0, EMF equals to 0. Then after that, you look at the remaining sections here, you can see that here my gradient is constant, therefore EMF is constant. Now the second part will be this one, the last part will be this one. This one here is gradient constant, because you see it's a straight line, but at the same time you see it's opposite direction. And also, what can you also say about the magnitude of the gradient here? Okay, what can you also say about the magnitude of your gradient? This one here, is your gradient here steeper or less steep? Okay, now in the first place, how do we judge whether okay, like if I ask you right now for this particular section that I just highlighted, how do I know when compared with this one, whether this gradient is going to be steeper or less steep? I mean, sometimes people can easily see it from looking at the graph.
Sorry. You can look. Can you use the gradient formula?
Yes, you can use the gradient formula. Yes, you are exactly correct here. You can use the gradient formula. We know that gradient is changes in y over changes in x.
Yep.
Okay, so now if I want to make a comparison between these two right now, let's just say I look at the change in x right now for both of them. I notice that the change in x for both of them is constant.
Yep.
Okay, so the change in x is constant right now. I can say that gradient is actually just proportional to the changes in y. So now when I look at the changes in y, this one is the change in y, and then this one is the changes in the y, right? Okay, so you see, I can clearly see that this length here is longer than this length. So here I can say that, since this changes in y is larger, this gradient is larger. So I can now say that, yeah, you have constant gradient, opposite direction, and the same time is larger magnitude, is steeper, so the magnitude is larger. So from here, your EMF would be constant, opposite polarity, or negative sign. Okay, opposite polarity, and then larger magnitude. So when you want to draw your graph of EMF versus EMF versus T, I will just draw it at the top right hand corner here, just to you see. It will look something like this. This one is say your EMF versus T. Your graph will look like this, like this, like this, like this, like this, and then like this. Something like this, okay? Because here, gradient 0, EMF 0. Gradient constant, EMF constant. Gradient 0 again, EMF 0. Gradient constant, opposite direction, but larger magnitude, so EMF is constant, opposite polarity, larger magnitude. Then this part here, gradient 0 again, so EMF is 0.
Okay.
Right, so this one is worth, I think, what, 4 marks here, just like that. Right, so we just match the timings accordingly. Right.
Do we usually need to explain the
do you need to like explain like what I just wrote on the board here? No need to.
Okay.
No need to. The ones that I just wrote on the sides of the screen right now, you are not required to like write them all out to explain. No need to. All you just need to do is to draw the graph shape, which basically looks like this one here. Okay. That's all they want to see. If you have drawn this correctly, that's where you get your all your marks. Okay. When they give the mark, is based on how you drew your graph, not based on your explanation. Okay. Right.
Yep.
Okay. So just draw it out. Now, sometimes you may be wondering also, what if I drew my diagram slightly differently? In meaning to say, what if I drew my diagram like this, where I say that this one is 0, but this one is negative, then 0, then this one is positive, then 0. Now, in cases like this, you will still be marked as correct. No worries. Okay, because sometimes people will be asking, should I always start with positive first, or can I also start with negative? It doesn't matter. You start with positive, you start with negative, it's fine. The important thing is that you are showing the EMF as having opposite polarity. If this one is negative, and this one is positive. This one must be shown as positive and negative. Okay, as long as you sure that they are having opposite polarity, that's where your other mark came from. Okay, right? So this one is okay. Now you see in your case here, this one here, the EMF values were not given. You don't really need to show the values or mark the values inside. But the example that you did under page 12, the one that we did in the last lesson, which was this one, you notice that it's also drawing something like a graph, page 12, okay? That one was the last example that we did in the last lesson. The graph that we drew was somewhat similar, okay? This one is actually page 12, which is an example that we did in the last lesson. Now, in your example here, this one, you were drawing a graph. All right, this one was worth 4 marks or so. But because your questions in the previous questions for this same question, they already asked you to calculate out the EMF and they give you some values. When you draw your graph, you need to indicate the values. Like you see in my case here, I draw the EMF, I indicated as 4 millivolts, and then for this one, I indicated as -2 millivolts. So in cases where they give you values, and then after that, your graph drawing seems to have a lot of marks allocated to it, they expect you to indicate the values. Okay, so just bear that in mind. In your case here, you don't need to, the current one that you're looking at in page 20, you don't need to indicate because there's no values given whatsoever. All right.
Okay.
Okay, so this one is okay. Then after that, let me just go on to some other one. Okay, we've done page 20. We can probably go to page 27 and have a look. Okay, yeah. So next one we can look at is page 27. Okay. Let's have a look at page 27. Okay, so let's just have a look at that while I'm going to rub off everything else here.
I'm done.
Okay, right. So they ask you to define magnetic flux. Okay, I think it's better if I just erase everything. I'll make a lot things a lot simpler. Okay, define magnetic flux. Magnetic flux here is asking you to define this one, the phi equals to BA. Okay, so this one is magnetic flux. If they have magnetic flux density, then it is B equals to FB over IL. So there's a difference in whether it's magnetic flux or magnetic flux density. They actually refer to different things. Okay, so this one, magnetic flux is phi equals to BA. This is March 2018 P42. You know, this one will be question 10. Okay, now define magnetic flux. Magnetic flux is simply the product of magnetic flux density and the area perpendicular to the flux. That's all there is to it, right? So then state Faraday's law of electromagnetic induction. It is simply saying that the magnitude of induced EMF is directly proportional to rate of change of flux cutting or rate of change of flux linkage. All right, okay. Okay, so this one is okay. Then we look at part B again. Part B may seem a bit familiar. Okay. Or part B may seem a bit familiar. This one is regarding calculations. Okay, look at part B. You have a solenoid that has a coil C, that is a wire that is wound tightly about its center. The coil C has 96 turns. A uniform magnetic flux in Weber in the solenoid is given by this expression, where I is the current in amperes of the solenoid. So calculate the EMF induced in coil C when current of 3.5 amps is reversed in the solenoid in a time of 2.5 milliseconds. Right, so from here, let's look at this one first. If you look at the diagram, there's actually two different solenoids here, or rather two different coils. The first one is actually this one, this blue colored section here. We know that when current runs through it, the solenoid, you're going to produce a magnetic field around it. Okay, but at the same time, you also have another solenoid that's wrapped around the existing solenoid. This one is actually called C here. Okay, so called C is having flux linkage through itself. Okay, so right now the question is asking you, if in the first place I had a current of 3.5 amp, and then I changed the current to negative 3.5 amp in a time of 2.4 millisecond, what is the EMF induced in the solenoid, in the coil C? Okay, now you might be thinking, well, the magnitude is the same here. Just now, one of the main things that we were able to do was that we know that I is proportional to B, and then after that we say that B is proportional to, and then after that we also say that B is proportional to flux linkage, and then from there we also say that I is therefore proportional to flux linkage, right? This is one of the relations that we did just now. I know that I is proportional to B, B is proportional to flux linkage. So the end conclusion was that current is proportional to flux linkage itself. Now, the thing here is this. This one, I know that if I is increasing, flux linkage is increasing. I drop, flux linkage is dropping. I is constant, flux linkage is constant. Okay. Now from here, you can also say that if I change direction, flux linkage also change direction. So if let's just say right now I have the current that is indicated by these red arrows here, I could have a magnetic flux linkage that is at a certain direction. Maybe say it could be like this. But then the moment I change my current direction, so rather than flowing in the red direction that's shown here, is now flowing in the opposite direction to the red colored line. So I will still have flux linkage, but this time my flux linkage will be flowing in opposite direction. It could probably be flowing, my flux linkage could probably be directed in this direction. Okay, so there is change in flux linkage here because the direction has changed. So you're going to have EMF induced. So the question is just asking you, what is the EMF induced then when I go and change the current direction? So this one, you will probably have to look at it from the original equation for flux linkage for EMF. You know, we know that EMF is rate of change of flux linkage. Okay, now in my case, I can actually say that because my n is constant, my n can be taken out. So I get flux linkage divided by, sorry, this one I get rate of change of flux only. Okay. Now, the equation that you have before this was just telling you flux is what value at a certain current value. Okay, so here, if flux is 6.8 times 10 power minus 6i, change in flux would be 6.8 times 10 power minus 6 times the change in current. Okay, so this one is one relation that you can actually see from the given equation, right? So that change in flux that you have can actually be substituted here, where you instead say that your n is 6.8 times 10 power minus 6 times with the change in your current divided by your time, the change in time. Okay. So in your case, what do you suppose is the change in your current? Your change in your current would be something like this. Because originally your current is, say, 3.5 amps. This is 3.5 amps. This is a graph of I versus T. This is a graph of your 3.5 current versus time. 3.5 amps suddenly changed to negative 3.5 amps in the time of, say, 2.4 milliseconds. Now your change in current is actually this one. Okay, 3.5 to negative 3.5 is actually just going to be 3.5 times 2, right? Right? So that's why here you can actually just say that your current is 2 times, change in current is actually just 2 times or 3.5. Okay, so your working looks like what you see on the screen right now, written in pencil there. Okay, right? So you're going to get the EMF as 1.9 volts. Okay, so you're going to get the answer as 1.9 volts. All right, then for part C, the DC supply, okay, before I move on, this one you copy already, and this one you understand?
Yep.
Okay, right. Okay, part C is actually from the next chapter, which is AC circuit, but this one I'll just explain it a little first. They tell you the DC supply, DC here refers to direct current, is now replaced with a sinusoidal alternating supply. Now, when they say DC supply is direct current, you can just visualize the current as being something similar to this direct current. There's no change in the direction. There's just positive current throughout or negative current throughout in some cases. It doesn't change. In your case, when you have sinusoidal alternating supply, what it means to say here is that your current actually looks like that, like this. Your graph of current versus time now looks like this. Okay, you'll notice that your current keeps changing direction because you have positive and negative throughout as time keeps running. And when it is sinusoidal, it just means that the variation of current is curved in like this. Okay, so here the simple answer that I can just mention to you here is this. We know that when current change, your flux density change, flux linkage change. But the end conclusion here is that when current change, flux linkage change. So right now, if you look at the graph of I versus T that I drew on the top bottom right hand corner here, this is a graph of I versus T. A graph of flux linkage versus time will also look like the same here. Okay, so you see the variation of flux linkage versus time that you have here is sinusoidal in nature. The EMF that is induced would also be alternating. Here the answer was just that the EMF induced is alternating with the same frequency as the supply. Okay, the important thing to just note here is that if I have sinusoidal alternating supply, my current is varying like this. Because my flux linkage is continuously varying, following the same graph, I also have continuously changing flux. I also have continuously changing EMF. The EMF that I'm gonna get will continuously vary, and you also be sinusoidal like this too. Okay, so we'll just say that the EMF induced is alternating also. Okay, but with same frequency as the supply. All right. Okay, so this one just take it as it is first. When we go to AC circuits, we'll have a better understanding of what this one means. All right, for now, it's just alright to understand the concepts. Okay, right. So that one is okay. Then next one, page 31. Let me go on to page 31. Okay, 31 is something like this. Okay, have a look at page 31, all right? Let's have a look at page 31. Page 31, June 18, P42. Okay, June 18, P42 would be this one. Number 9. Okay, state what is meant by magnetic flux linkage in your call. Okay, this one is asking you about magnetic flux linkage. The previous one that you did was asking you about magnetic flux, where you say phi is equals to BA. When it comes to magnetic flux linkage, we already know it is N phi and BA. So you're basically trying to define that now. When you say magnetic flux linkage is number of turn or calls multiplied by magnetic flux density multiplied by cross-sectional area when the magnetic flux density is normal to the area. This one is worth 3 marks. Okay.
Mhm. Okay.
The word here where you say is normal to the area, that one is required. Okay. Right. So I'll let you copy a while, then let me know when I can move on. Go on for a while. Let me just give me a second. I need downstairs. So yeah. Okay, right. So okay, 9A, all right.
Yeah.
Okay, so now let's look at part B. For part B, you will call a wire that has 160 turns and a diameter of 2.5 centimeter. The coil is situated in a uniform magnetic field or flux density 7.5 millitesla as shown in figure 9.1. The direction of the magnetic field is along the axis of the coil. The magnetic flux density is reduced to 0 in a time of 0.15 seconds. Show that the average EMF induced in the coil is 3.6 millivolts. All right. Okay, so here, they're already showing you your magnetic field, which are these lines here. And then after that, they show you that you also have a coil, which is this one here. Your magnetic field or magnetic flux is passing through your coil. So you have flux linkage here. That one we know. Okay, now then after that, they mentioned to you that the magnetic flux density is now reduced to 0 in a time of 0.15 seconds. So it came to a case where you have flux linkage to no flux linkage. So here, this means that you now have change in flux linkage here. Okay, so you have change in flux linkage. You have EMF induced, or rather voltage induced. That's what the question is trying to ask you right now. Show that the average EMF induced in the coil is 3.6 millivolts when they suddenly reduce the magnetic flux density to 0. Okay, when your magnetic flux density is reduced to 0, your flux linkage is reduced to 0, because we also know this relation from the earlier equation where it tell you that N phi is NBA, flux linkage is proportional to B. Okay, so based on that knowledge, we work through it. We know that EMF is equals to rate or change of flux linkage. We go and expand it out. Change of flux linkage is change is in NBA over delta T. Now, what is constant here? The constant here is your N. It never changed. The cross-sectional area A also never changed, so I can take that out. So my expression becomes NA delta B over delta T. Okay. So now, if I ask you what is my delta B, my delta B is actually just 7.5 millitesla. My delta B here is actually 7.5 millitesla minus 0. So giving me 7.5 millitesla lah, all right? Because it was originally this value is now reduced to 0. Okay, and then when I want to find out my cross-sectional area, the cross-sectional area is this one here. Okay, A is pi over 4 d squared. So I use d because I'm given diameters, so it makes my life simpler. So that's why my equation now becomes n times pi over 4 d squared, because it is cross-sectional area, times delta b over delta t. Then the next thing I just need to do is to sub in everything, and I'll get the answer. Okay, so you're going to get the answer as 3.6 millivolts, just like that. Okay. Right. Okay, so then this one, I move on to the next one. Okay, this one talks about graph drawing. Okay, then okay, so this one talks about graph drawing. They tell you now the magnetic flux density B in the core is now varied according to time as shown in figure 9.2. This was the variation of your flux density with respect to time. They now ask you use that same data to show on the next figure the variation with time of the EMF E induced inside the core. Okay, so just now I already mentioned to you, if your flux linkage is NBA, flux linkage would actually be proportional to B. All right, so now this one is a graph of flux density versus time. But since I know that flux linkage is proportional to B, a graph of flux linkage versus time will follow this same shape. Okay, right? So then I know that EMF is rate of change of flux linkage. So in my case, yeah, I can actually just say as this. This one is just another way of doing the same thing. Okay, wait, let me just erase it, because what I wrote here is a bit different from what I'm trying to explain. I know that EMF is change in flux linkage over time. This one would just be the gradient of flux linkage versus time graph. Okay, so I can prove that from here, EMF is actually the gradient of my flux linkage time graph, which is actually going to follow this same shape here. So here, I really just want to see my gradient. That's all. Okay, so there are some things that you can see from here. This one here, gradient 0, EMF 0. Gradient 0, EMF 0. Gradient 0, EMF 0. Then the next one will be this one here. Okay, this one is gradient constant. That would mean that your EMF is constant. Now, if you look a bit more to in the previous part of your question, you would notice that you actually already found out the value of the EMF here. Because you see this one here, if you look carefully, this value here is 7.5 millitesla. And then this one here is 0 millitesla. And it occurred at a time of what, 0.15 seconds. Isn't this what you were doing over here? You actually calculated it out already. So here, although the question never really specifically mentioned to you that the EMF that you calculated was from this particular blue line, you're supposed to know is from there. Okay, just by looking at how the flux density change. Okay, so that's why here I know that my EMF is going to be 3.6 millivolts. And then the last one, this graph, this part here, I know that the gradient is constant. Now this one, did your gradient change direction? If you look at the yellow colored line that I just highlighted, did your gradient actually change direction?
Yes.
Okay, no, it actually didn't.
Wait.
Change direction will be when it looks like this.
Oh.
Okay, so yeah, this is one common mistake that a lot of people tend to mistake. When you're looking at gradient, you're looking at, how to say, gradient. If I have something like this one is considered to be positive gradient, right? But then after that, if I have something like this pointing down, this one is negative gradient. So this one here, because you guys, a lot of people see that, or this line here, the yellow color line is below the x-axis, then somehow or another they kind of assume that is opposite direction. No, that one is not the way to look at gradient.
I
Okay,
see.
so
Okay.
that yellow line here actually did not change direction. They are both still pointing downwards. In other words, they still have negative gradient here. Okay, so direction wise they never change. Okay, the ones that we did before these 2 or 3 examples before this, they actually changed direction, but this one in itself they never changed. Okay, so this one just bear in mind, no change in direction, no direction change. Okay, then after that we also can evaluate whether this one is, how steep is this line with respect to the blue line. We can actually say that this line is going to be twice as steep. Okay, so your EMF is constant and your is double. If originally is 3.6, now it's 7.2. Okay, now for this one, how do I know that the gradient is double? It's somewhat similar to what we just did earlier when we said that gradient is change in y over change in x. When I look at this one, the change in y, and this one, the change in y, they're exactly the same. So in my case here, change in y constant, my gradient is actually inversely proportional to changes in x. So now when I look at the changes in x, I can actually see that this change in x versus this change in x, this one is half of what you have here. Okay, in other words, the change in x here is reduced by 2 times. So if my change in x is reduced by 2 times, my gradient would increase by 2 times. That's why here I can say that it is actually twice as steep. So my EMF is 7.2. So now when you want to draw your graph, it now looks like this. This one I believe is quite, yeah, it's still 4 marks. Okay. So your graph would essentially look like this now. Let me just erase off the unnecessary stuff. Your graph now looks like this. Okay.
Okay.
And they've actually made your life easier also because they actually label the values on your x and y axis so that you can easily plot out the values. Okay. So this one is okay. Right. So this one, okay. Now then after that, this one is, what page was this? This one is page 31. There's 2 more questions. Then after that, we can probably move on to something else. Next one is 33. This one is 33. This one is graph showing whole probe and yeah, things like that. Okay, so let's go with this one, page 33. Okay. This one is November 2018 P41. Okay, the one that asks you to state Faraday's law, Faraday's law of electromagnetic induction. This one I think we'll skip because we've done it a few times already. Just copy the definition from the notes. Right, now look at part B. A solenoid S is wound on the soft iron core as shown in figure 9.1. A core C having 120 turns of wire is now wound onto one end of the core. The area of core C is 1.5 centimeters square. Core C is actually this portion here that you're looking at. Core probe is placed close to the other end of the core. When there's a constant current in solenoid S, the flux density in the core is 0.15 Tesla. The reading on the voltmeter connected to the Hall probe is 0.20 volts. The current in the solenoid is now reversed in a time of 0.13 seconds at constant rate. So calculate the reading on the voltmeter connected to coil C during the time that the current is changing. Right, so there is actually three different portions here, three different parts here that you can see. The pink colored line here, pink colored section here, which is connected to a voltmeter. The green colored section here, which is connected to a hole probe. And lastly, the blue colored section here, which is connected to a power source. Right, there's actually three different distinct parts here. Okay, so now they tell you, okay, now before we go to this one, wait, calculate the reading connector on consider the time that the current is changing. Okay, so they tell you now, the switch is closed. They didn't say the switch is closed, but they say that there's constant current flowing through the solenoid. Constant current flowing through the solenoid. This means that I would have a magnetic field being produced through the solenoid. Okay, so you see your magnetic field just so happens to pass through your coil C, giving it flux linkage. And then your flux magnetic field also passes through your hole probe. If you recall what we did in the previous chapter, hole probe just measures to us the flux density. It tells us how strong is the magnetic field, and it normally gives us the reading in the form of hole voltage. So your hole probe here connected to a voltmeter is actually measuring your magnetic flux density and giving it out in terms of hole voltage. All right. And then your coil C here, which is actually a separate part, is connected to a voltmeter. Okay. So now you see, when your current is running through your solenoid, we know that you're going to have a magnetic field. You're going to have flux in your magnetic field in a certain direction. You will also have flux linkage in a certain direction. So now they tell you that the current is now reverse. So when current is reverse, that would mean that the direction of the magnetic field or your magnetic flux linkage will change, right? So this one here, you will have change in flux linkage. Therefore, EMF will be induced. Okay, right? So now the question is asking you to find out what is the reading on the voltmeter connected to coil C during the time that the current is changing. Your voltmeter connected to coil C here is actually measuring your EMF or your voltage induced, right? So that is the understanding here. So we are going to start off with the equation for flux linkage, which is delta change in flux linkage over time. Same thing as before. Now then from there, we are going to multiply. And then from there, we're just going to sub in the values. Now, if I ask you the flux linkage versus time graph, it by right would look like this. Okay. Because let's just say right now, this one is for current I. This one is for negative I. Okay. We're talking about the flux linkage through the coil. If I have a current in one direction, I, this is my flux linkage. But then if I reverse the current direction, this is now my flux linkage. It has changed direction. And this occurred in a time of 0.13 seconds. Okay. So my flux linkage change here is actually 2 times of, and my flux linkage change here is actually just twice the original flux linkage. That's why here you see that there's a 2 multiplied by 2.
Yep.
Okay. So I take the number of turns multiplied by the flux density multiplied by the area multiplied by 2. This one in itself is actually my NBA, which is the same as my flux linkage.
Mm-hmm.
So I need to multiply by 2, then I divide by the time. Okay, then I'll get this answer. Right. Now from here you should be able to see something. There's something like a pattern. Whenever they say something is reversed, the current is reversed, or some direction is reversed, notice that you always tend to multiply by 2. Okay, so this is one hint there already. Normally you see from the questions that you've done, if you notice that they say something is reverse, current reverse, or some magnetic flux density, magnetic field is reversed, you should, most of the time you notice that your working needs to multiply by 2. All right. Okay, so that one is okay. Then you move on to the next page. The next page here talks about something else. This one is asking you to fill in the tables. Right, so let's look at the table here. They tell you that complete figure 9.2 for voltmeter readings for the times before, during, and after the direction of current is reversed. Okay. They tell you 3 things: before current, during current change, and after current change. And then they ask you, what is the voltmeter reading on hole C? What's the voltmeter reading on hole probe? Okay, so if we just single out the hole probe one first, hole probe one seems to be the easiest one to do. Before current change, it was 0.20. Okay, because your current is constant that time, your magnetic field is constant, so your flux density will be constant. I mean, okay, let's not talk about the thing being constant. Just know that before the current change, there's current running, there's magnetic field. You can actually measure the flux density there, with whose value is 0.2. Now, when you have current changing, that point where your current change is where your current is 0. So you have no magnetic field. So when you have no magnetic field, if you put your hole probe there, you're not going to be able to measure anything. It's just going to be 0. Then after that, after current change, you still have the same current flowing through, but it's acting in the opposite direction. So your magnetic field that's produced would also be acting in the opposite direction. You're going to get back the same magnitude, just that the direction is opposite. Because your flux, your magnetic field is opposite direction now, you go and put your hole probe there, you're going to get a negative sign, opposite polarity. All right. Okay.
Yep.
All right. Then you look at the first line, the one for voltmeter connected to coil C. Now, before your current change, you don't have any change in flux linkage yet. Okay, so your voltmeter reading is going to be 0 because no EMF induced. EMF can only be induced when you have change in flux linkage. Before your current change, it was just constant current flowing. So it's just constant, it's constant current flowing. You will have constant magnetic field, constant flux linkage. So no change in flux linkage, no EMF induced. But during the time when your current changes direction, the current was reversed. We know that your flux linkage changed direction already. So you had change in flux linkage, you're going to have EMF induced. That value will be this one, which is the one that you calculated in the previous part of the question. Okay. Then after your current has changed direction, it maintains at that value, you are going to have constant magnetic field, constant magnetic flux, no change in flux linkage. So your EMF induced is just 0. There's no EMF induced. Okay, right? So this one is okay. Right, so that one okay. Then after that, 34. You can look at page 34. Let me see whether 34 is actually the same thing that you just, that's the same thing that you're looking at. Okay, 34 this one I think is a simple exercise. Okay, November 18 P42.
Yep.
Yeah, it's on the page that you're currently looking at.
Yes.
So they give you something like this. They tell you that the hole probe is placed near one end of the solenoid that has been wound on the soft iron core. The current in the solenoid is switched on. The hole probe is rotated until the reading VH on the voltmeter is maximum. The current in the solenoid is then varied, causing the magnetic flux density to change, according to what the graph here show. Then after that, you look at what they say. This one is the magnetic flux density versus time for the solenoid. Okay. So they ask you right now, when they change the magnetic flux density, this is on the second page. Yeah, sorry. Yeah, part B, they tell you the hole probe now is replaced by a small coil or wire connected to a sensitive voltmeter. The hole probe is taken out, they replace it with a small coil or wire. The flux density normal to the coil is again varied as shown in figure 9.2. Your magnetic flux density is varied the same way as before. So show the variation with time of the EMF induced in the small coil for time 0 to T4. So just now your magnetic flux density, the pattern look like this. It look like this. Okay. Right. So this one was graph of B versus T. So your magnetic field passes through coil C, and the flux density of this magnetic field varies according to this. Okay, so this flux magnetic field passes through coil C, you're gonna have a flux linkage through coil C. So simplifying everything, we know that flux linkage will be proportional to B. So a graph of flux linkage versus time would also be same shape. And then EMF is rate of change of flux linkage versus time is the gradient. Okay. So this one, I think not so much issue with this. Gradient is 0. EMF is 0. Then this one, gradient constant, EMF will be constant. So all in all, your graph here looks like this one, like this, like this, like this, like this, like this. Okay, all right. So simple enough. So you think, despite all the explanations, when it comes to drawing the graph, the only thing that you were really using all the time was just really looking at the gradient. Okay, right. They tell you that you have a small coil that is situated in non-uniform magnetic field as shown in figure 10.1. The coil consists of 40 turns of wire and moves at a constant speed in a straight line. The coil has displacement x from point P. So you have a displacement of x from point P here. The variation with x of the magnetic flux in the coil is shown in figure 10.2. Okay, this is the variation in flux of the coil shown by this graph here. So they're asking you right now, the coil is moved at constant speed between P and point where x is 3 centimeters. So in other words, what they're saying here is that they're moving it between here to here. So they ask you to calculate the change in magnetic flux linkage of the coil. So what you have here is actually just the change in flux, because this is a graph of flux versus time. So here, if you calculate this one out, this one is just merely the change in flux, not the change in flux linkage. The question wants flux linkage. So you know that if you want to find out the change in flux linkage, you actually need to multiply with n. So here you just take the number of call turns, which is 40, multiply with the change in flux, then you get your change in flux linkage as 8 times 10 power minus 5 Web. So that one is okay. Now then after that, the other part, they are asking you right now, find out the EMF induced, they tell you right now the EMF induced in the coil is 5 times 10 power minus 4 volts. Determine the speed of the coil instead. So we know that EMF is always rate of change of flux linkage. So EMF here is 5 times 10 power minus 4. The change in flux linkage we found earlier is 8 times 10 power minus 5. So we can find out what is the time that it took for the EMF to be induced. That one took us 0.16 seconds. Okay, so they want to find the speed. If you want to find the speed, speed is actually just distance over time. We know that the EMF was induced over a distance of 3 centimeters and it took a time of 0.16 seconds. So if we take this divided by this, we're gonna get the speed as 0.188 meter per second. So that one is pretty straightforward here. Okay. Then on the next figure, they ask you to sketch the variation with X of the EMF E induced in the coil for values of X0 to 6 centimeter. Okay, so this one here, the end conclusion is that you're still going to be looking at the gradient. But why specifically at the gradient? This one, let me just explain it a little. Okay, now this is a graph of flux versus distance. Okay, this is a graph of flux versus distance, not time. A lot of the graphs that you done just now was talking about time. This one they say is distance. But there are a few things that we can do from here. The end result here is that I just want to say that this graph of flux versus distance is actually equivalent to a graph of flux versus time in terms of the graph shape. Okay, so why can I say that? That one is because I know that distance is, I know that speed is distance over time. Because the graphs, the question said that you're moving at a constant speed, v is constant, that means x is proportional to t. So that would mean that if I have a graph of flux versus x, the graph of flux versus time would be the same shape. Okay, then EMF is rate of change of flux linkage, and I take out times with change in flux. So EMF is proportional to change in flux, rate of change of flux. So the EMF is proportional to gradient of flux time graph, which is based on this. Okay, so there are ways in which you can explain it, in which you can say that if you have a graph of flux versus distance, it's going to be the same as flux versus time. Okay, and at the same time, the gradient of flux versus time will be the same as your EMF. Okay, so here you will notice that you're really just going to be looking at the gradient again and nothing else. So this one here, I noticed that gradient is constant, EMF is constant. The EMF is going to be 5 times 10 power minus 4 because this one is really stated for A part 1 and part 2. Then after that, you look at the opposing gradient, which is this one here. This one here, your gradient is constant, opposite direction, but twice the magnitude. Okay, you see that for the same x distance, this change in y is double this change in y. So this one, your gradient is going to be double. So twice the magnitude. So your EMF is just going to be negative 10 times 10 power minus 4. So when you want to draw your graph, it will just be something like this. Where this one is 5, this one is negative 10. That's why your graph shape now looks like this. Okay. Yeah, but in your case, you don't need to do until that detail, because here you see your question, you look at the marks that has been allocated to it. This one you only allocated 2 marks, not 4 marks, unlike the previous questions that you've done. So they don't really expect as much details. I mean, okay. So if let's say you took the effort to purposely write down on the graph, this one is 5, this one is -10, that one will be okay. But that one won't be credited because the marks given here are quite limited. What they really just want to see is this magnitude is larger than this, that's all.